All right, so where we left it was at this point where we said we will reject the null hypothesis that all the means are equal. Now, here are all the means we observed, and these two look very close together. What has caused us to reject the overall hypothesis? Now, remember, the overall hypothesis was that all the means were equal. So we could, so mu1 equals mu2 equals mu3 equals mu4. So any one of these equalities here could be causing us to reject the whole. Okay, so sometimes we would like to know, are all of these unequal, or maybe could we consider some are equal and some are not? And we said, well, we can't test all mu I equal mu j because that's too many to do, and then we would wreck our 5% alpha. So we're stuck. What to do? And the answer is there is something we can do. And first of all, note that I added this little bon at the end of the one-way command. So the tab gave me this part. What did the bon give us? Well, let's take a look at what is this problem of doing all this testing. It's called the BONFERRONI correction. There are others. This one is very conservative, and so this might be a good reason to use it. If we wish to perform all possible pairs of comparisons, so for example 1 versus 2, and 1 versus 3, and 1 versus 4, and 2 versus 3, and 2 versus 4, and 3 versus 4, all of them, you want to do all of them, okay? One way to do that is to take your alpha, let's say 0.05, and divide it by k combination 2. So in this case, k was 4, so k combination 2 is 6. So divide it by 6, and then test each one of these comparisons at this level, at the alpha star level, to have an overall level of alpha. Or if you multiply by k combination 2, there's your overall alpha. And this is what Stata reports for us. So what that bon did when we ran this command with Stata is give us this table. And what we've got here, we've got these couplets, and the top number is the contrast between 1 and 2. So it's the row mean minus the column mean. In this case, it's 0.0372. So it's the mean at 1 minus, it's the mean at 2 minus the mean for the first group. And underneath it is the overall alpha. So this is saying that the overall alpha is like 1. So you would not reject the hypothesis that these two are equal. This one, that 3 and 1 are equal, the alpha at which you would reject that is 0.094. So if you're doing an overall alpha of 0.05, you don't reject this one either. If you're doing an alpha of 0.05, you don't reject the 1 and 4 either. This one you do reject, because this is less than 0.05. So the 2 versus 3, you do reject. The 2 versus 4, you don't reject, so that's okay. And the 3 versus 4, you do reject. So these are the two that you would reject at the 5% level, namely 2 versus 3 and 3 versus 4. So let's look back there and see it. So it's 2 versus 3 and 3 versus 4. So what this is saying is that 3 is significantly smaller than 2 and significantly smaller than 4. But it's not significantly smaller than 1, and all the others go hand in hand, are not rejected. So 1 is not significantly different from 2, and 2 is not significantly different from 4, etc. So the one that's sticking out is women who are not hypertensive. They're not significantly different from men who are not hypertensive, but they're certainly significantly different from women who are, and men who are hypertensive. So that seems to be what's causing the overall rejection. So this is post-analysis of variance. We can do a BONFERRONI. And as I said, there are other ways of doing this. This is the most conservative one. And there it is.